Thanks very much.
Excellent. Okay, thank you so much, Adam. Yeah, first off, I just want to say thanks to the planners, Adam and Ralph and their teams for inviting me today to do the keynote for the eSim conference. I can say one of the really big disappointments, I would say, of 2020 was not having that opportunity to come visit Vancouver and kind of the west coast of Canada, which I've never been to. So I'll still try to make it there. Hopefully 2022 is when maybe travel resumes for us. I've been stuck here in Singapore now for almost 18 months, so I'm getting ready to get out there. But yeah, let me dive into the topic today. As Adam mentioned, I'm a professor at the National University of Singapore. I'm going to cover various parts of the research that my team does, and also in collaboration with lots of entities around the world. I really want to dive into a kind of a topic that's probably near and dear to a lot of people's interest, related to sort of the areas of data science and machine learning, et cetera, AI in the measured data realm, and then the simulated data realm, which is the kind of the traditional white box or physics-based modeling that a lot of people do within eBPSA. So before I dive into it, there's a QR code here that you can scan. There's also a link, and I've also posted a link in the chat. There's lots and lots of links in the slide deck. So if you want to have the PDF slide deck as I go through it, if there's something that sparks your interest, go ahead and click on it. It's kind of the beauty of Zoom sessions as well. I tell my students that they can interact with their computer while they're listening to the lecture as well. So here we go. So the Building and Urban Data Science Lab, this is the team at NUS, kind of the core team that works on these technologies. We focus on all different aspects of data science and related to the type of data that you collect from both energy consuming systems and buildings, as well as systems that interact with occupants and basically improve their comfort and safety and things like that. About roughly a third of our group have a computer science background. Another third have roughly engineering, some sort of engineering background. And then the remaining third have some background in design or architecture. So we're kind of a very interdisciplinary group, which is something that I know a lot of universities around Canada also have groups and labs like this. So if you're interested also in some of our other projects, you can click on our, you can go to the Buds Lab website and learn more about those. If you're not familiar with NUS, a little bit about the department that my group is within. As of July 1st, we're having kind of a rebranding. We have a new name called the Department of the Built Environment. So we're really excited about that, to kind of align more with the international norms of describing the type of research that we do. We're kind of the sister department to the Department of Architecture, and we do a lot of the technical, kind of somewhere between engineering and architecture, very similar to a lot of you that are here today. We're also looking at the QS ranking, also ranking in the top 10 in the world in this particular area, which is pretty cool. Also, my group is part of a larger consortium of research groups within the Department of the Built Environment called the 5D Digital Building Technology Lab. So this is, there's about 5 or 6 total professors looking at technologies related obviously to connectivity and wireless connectivity in the 5G direction, as well as building information modeling, Internet of Things, and various types of data science and machine learning. So check that out as well if you're interested. So getting back to the topic at hand, white box versus black box modeling. So like I said, you've got maybe sort of the traditional realm of simulation, white box modeling using engineering and physics principles to develop predictions of the energy or performance that a building is consuming. And simulation is really the foundation for eBPSA, and so that's why that's really a key focus for a lot of the research that happens in our field. On the other hand, we have machine learning. We have kind of this wave in the last 10 years probably of data-driven modeling techniques or black box models. And black box models are you're creating a model using training data and then using that model to predict a test data set in a sense. And I personally have been involved in discussions and debates, and what is the future, which direction should we head in, how can we use these tools, how do they work together, and it's sometimes it's a debate in a sense, I would call it sometimes, and that's why you see these two characters here kind of duking it out to discuss or to figure out what is this quote unquote future. There are really good arguments to both sides, and I'll try to cover some of those from each direction. And I'll also try to dive into some of the interesting, directions that I think we can go towards bridging the gap between these two areas. And I want to start with an analogous research community or industry. It's not a perfect analogy, it's not a perfect comparison, but I do think there are a lot of similarities, and that is the domain of driverless automobiles or driverless cars, or sort of the automation of driving a car without a human driver. And so why I think this is similar is that it's a system, or it's a mechanical system, which is a car, that's usually operated by a human being on some sort of larger network of roads. And traditionally, there are both white box and black box models, ways to model the way a human actually operates a motor vehicle. So it's buildings in some ways are similar, that you have systems, you have humans driving those systems, and you have these contexts or sort of boundary conditions related to those systems. Everyone's heard of the driverless car R&D community, I'm sure. The thing that they really have going for them in the last 5 to 10 years is a really, really clear and very compelling objective for the integration of machine learning and AI into this context. And it's easy everyone understands it. It's a car that drives itself, right? Safely and in all situations, in all roads and everything. A driverless car is not useful if it's only going to be able to drive itself in certain roads. It's also not useful if it's not safe, if it's not better, at least as good as a human driver or better. So there's a huge potential to save a lot of lives. There's people who innovate in this area can probably profit from it heavily. There's a statistic that I found in Canada of the number of fatalities on roads. A lot of those fatalities are due to human error, and theoretically, a driverless car might be able to prevent a lot of those fatalities. So because of this clear objective, because of this very bold and clear objective, there's a lot of attention in this field of autonomous driving or driverless cars. This is a set of graphs from an issue of The Economist last June that shows, just this explosion on the left of investment in AI. On the right-hand side, you see the sort of steady growth of research in this area in AI. And then in the graph in the middle, of course, you see the different key sectors where AI investment has been spent, or is it planning to be spent, with autonomous driving being the #1 sector. This translates into a lot of investment money. So if you look at the actual numbers, this is as of 2018, this is a website that I found that has, they kind of aggregated the different press releases of the different companies, especially automobile companies, that are either spending or planning to spend money to develop driverless vehicle technology. So the statistic that they come up with is around $100 billion of investment currently and in the future. And for example, Volkswagen is one of the biggest, and they have, in the next 5 years, they want to spend up to $50 billion in this area. So really a lot of, because of this clear and compelling objective, there's a lot of focus on solving this problem. So I want to show a couple examples of this area. Let's go back to our black box versus white box modeling discussion. Let's look at a couple examples of companies that do it in slightly different ways. The first one is Tesla. Of course, everyone's heard of Tesla because they have products on the market that are cars, and you probably have seen them around or maybe even have one. Tesla has the opportunity, because they sell these vehicles, to install sensors and harvest data from those sensors from all of the vehicles that are out on the road. So they're able to train their autonomous vehicle models using real data. So they have a really strong data-driven focus in the modeling that they use to predict how a car can drive itself. 3 billion miles driven, self-driven miles. These are miles where the car is on auto drive. Of course, a person is still at the wheel, but they are not hands-on driving at that point. So 3 billion miles, and really accelerating in the past few years. Their next closest rival is Waymo, and they've driven 20 million. So far less amount of data collected as compared to their competitors in a sense. If you look at Waymo, which is the company that I just brought up, this is another sort of leader in technology. In fact, a lot of people say it's even one of the leaders in autonomous vehicle technology. If you look at them, they don't sell cars, so they don't have quite as good of maybe a situation to collect data. So they rely more on simulation environments. So they're creating these virtual environments where a virtual car is traversing a virtual context and encountering different experiences that are probably very normal, but also experiences which are not quite as typical in the real world. And their system is really heavily driven on simulation. They're able to drive 20 million virtual miles per day, and they've driven over 15 billion miles in their simulations. So even surpassing quite significantly what Tesla has done in the real world. So through this kind of investigation and research, kind of looking into this field and trying to understand what we can learn in the buildings community, I came up with a few kind of key takeaways. And if you look at the technology for both of these companies, they rely heavily on one or the other, but they use mostly both, from what you can sort of see from the way they explain their technologies on their websites and in different venues. So they're using different strategies as a key focus based on their core business and the data that they have available, but they're using both types of models, and they're converging the results of those models to basically come up with a final sort of model that sort of an ensemble of models that is driving the cars essentially. So, so translating this even more deeply into 3 topics that I want to talk about over the next 30-ish minutes, 30 to 40 minutes, is 3 separate areas related to things that I think we can learn from the self-driving car community. The first one being generalizability. So as I mentioned, the goal is that a car can drive anywhere. It's not just the car can drive in a certain neighborhood or city. Really the end goal is that the system is able to account for a lot of the stuff that you find in the real world beyond just these small areas, let's say. So there's a lot of what's called edge cases in this sense. So you're having to understand how the car is going to respond to a giraffe crossing the road, which probably is never going to happen. But if it does happen, the car needs to be able to respond to that. The second thing is black box modeling in the autonomous car area is really used, if the data is available, like it is for Tesla, it's used to really train those models in common situations, most of the common situations that the car encounters. On the other hand, white box modeling is really good at creating data when you don't have access to it, which is something like what Waymo does, but also situations that are not quite as common, or it's just impractical to get data to train models. So these are things that we can learn from in general, and then really diving into even more specific details. So I have 4 sort of sections, generalizability being the first one. Second one really focused on the black box modeling side. How can we collect more data? How can we use more and better data in our research? I'm going to bring it back to the research side of things. And then simulation, so larger scale simulation frameworks. So simulating lots and lots of buildings and trying to basically move into that sort of scaled simulation thing. And then finally, last but not least, kind of the conclusion is So how do we get $100 billion in investment in this community? So not really research money. Research funding is part of that, but how can we get the big multinational companies in our community, in our field, you know, the Siemens or the Johnson Controls or some of these big companies to start really investing heavily in AI technology or machine learning the way that car companies have been doing. So let's dive into the first topic. The first one is model generalizability. And this is, once again, this is focused, just want to be very clear, this is kind of the strong focus on the black box modeling side, the data-driven modeling side. This is something that, just to preface this, that other research communities that use machine learning are also uncovering some of the things I'm going to talk about in terms of generalizability. There's a couple, there's a list of 3 links here that I think are really interesting. They're very contemporary. One of them came out May 29th, so just like about a month ago, less than a month ago. The other one is a Nature paper, which I'll talk about in the next slide. And they're really finding that the way machine learning is really used in research or in these publications has problems. There's a lot of problems that you know, probably not intentional problems in a sense. And they're just little things that make it hard for the research to be useful in the real world context by companies. And, you know, like I said, diving into one of these examples is in the medical field. There's radiography is, you know, computer vision and radiography is really something that's heavily researched, because if you can use if a computer can analyze a scan and detect COVID, for example, in this case, that's great. That's really useful. It can automate the process of detecting, maybe even save lives. But in this study, they found they sort of filtered from over 2,000 studies down to about 400 studies after screening, really doing another round of screening, getting down to 62 studies. And they really found, even out of those 62 studies, none of the machine learning research in those studies is potentially useful in a clinical setting, due to methodological flaws, due to problems with the data sets, due to the size of the data sets, due to the fact that, yeah, just various issues. So this is really interesting. This is telling in that community. And the authors, I think, in the articles that in the links that I put before as well, you'll notice that they do explain that they don't think that these are intentional flaws. They don't think that most of the people or all of the people are probably doing these things on purpose. It's just there's a disconnect between what's useful in practice and what's happening in the research community. So let's bring it back to our community. So this is something I've been kind of passionate about for a few years. There's a paper at the bottom here you see that outlines this, and this is one of the graphics that's not in the paper, but it's in the data set that accompanies the paper. In the building industry field, we love case studies. And I'm no different than probably everyone else here. I would say a lot of the work that I've done in my research career is focused on a certain case study. So you have a building that you have access to, that you can collect data from, you collect those data, and then you create some, you know, really cool algorithm. You build some model, and that model in your paper is really good. I mean, you say it's fast, it's accurate, whatever it is that your objective is, and you're probably also creating a benchmark a lot of times to compare it against and things like that. But the problem is that we just cannot understand the difference between these case studies. It's very difficult to do this, and this is something that I think is related to some of the problems that you're seeing in these other communities as well. I did a little bit of and through this paper that I published in 2019, I did a little bit of an investigation of one of the biggest reviews that came out in the last couple of years, last few years, which is a review of a lot of prediction papers. These are energy, short and long-term energy prediction papers using machine learning techniques. And out of all of these publications, I filtered out the ones that used real data. They didn't use simulated data, but they used real data. And 33 out of the 42 papers were using data from a single building, right? So our case study nature, the way we really like to do research in the building industry, is making its way into the way we do machine learning, applied machine learning research. And so my mission really has been, okay, how do we start to bring, we've applied every model you can think of, random forest and deep learning and you know, all the cool models that you can think of. We've even innovated in some of these models, but how can we take it a step further and say, what is a modeling technique or method or workflow which is scalable, which is generalizable? How can you use this technique across numerous buildings instead of just single case studies? So this is something that the machine learning community as a whole, they find this very important. And it's something that that's been kind of one of the parts of this mission, is to try to get our research community to really mix more with the larger data science community, to learn some of these lessons and to cross-pollinate different ideas. And really the goal is then that we start having these data sets that people you can create your amazing technique. I can make the Clayton technique, and I can apply the Clayton technique to a data set that other people have applied their techniques to. And we can really show that my technique is more accurate, maybe it's faster, maybe it's whatever that objective is, but we do have that basis of comparison. And that's really interesting and useful from the machine learning innovation part of our research community. So in order to move forward with this in 2018, 2019, I got heavily involved with a large team. It wasn't just me, I was one of the technical leads, but it was a larger team of folks, which I'll mention in the acknowledgements at the end. We got together, and a lot of the people were from ASHRAE, from the ASHRAE TC 4.7 committee of ASHRAE. And we got together and decided, let's do something in this direction of generalizability. We came up with a plan for what was called the Great Energy Predictor 3 competition. You can see the link there. You can go and check out the page for the Kaggle competition. Kaggle, if you're not familiar, is a website that has dozens of different competitions from all kinds of industries, usually finance, medicine, marketing, advertising, kind of the more traditional markets that are good at applying AI and machine learning. And we were able to convince ASHRAE to support this, to put up $25,000 of prize money. And we as a technical team put together a data set of about 2,400, almost 2,400 whole building energy meters from electricity, chilled water, hot water, and steam from about 1,500 buildings from about 16 locations from mostly North America, but a few from Europe. And so one of the largest data sets of its kind, and the largest competition, machine learning competition of its kind. And I'll talk a little bit more about the data set and the competition context here in a second. So the contestants in the competition were downloading a training data set of hourly whole building meter data for 1 year. And they were training machine learning models using that and weather data and uploading those data to the Kaggle website. The Kaggle competition itself was about over 60 days, over 2 months, and you could upload multiple predictions. You could upload up to 2 predictions per day. You could join forces with other participants and create teams of up to 5 people. And there was a constantly changing leaderboard. It was called the public leaderboard. So during the competition, the leaderboard would be changing day by day based on when people uploaded their predictions. And those predictions were instantly scored on the platform. And one thing I forgot to mention is that the reason that this is a Great Energy Predictor 3 competition, you might wonder, is that ASHRAE actually had 2 competitions in the mid 1990s. So this is over 25 years ago that we had the first versions of this type of competition before the internet was really a big thing. This was a team from Texas A&M and University of Colorado that were mailing floppy disks across the US to participants who wanted to sign up. Now, 25 years later, with the internet and things like Kaggle, we had a much easier time attracting participants. We had over 4,370 total participants. They grouped into various teams, about 3,600 teams from all across the world. And as I mentioned, they're able to upload multiple predictions per day. So over almost 40,000 total predictions was uploaded over that time frame. The winning teams you see here, these are the prize money was for the top 5 teams. You can see various locations from across the world, as well as expertise and background. Most of the people were professional data scientists or students in engineering, but a lot of them had actual engineering or building sort of metering experience, which was really fascinating and seemed to be very helpful for their solutions. The top 5 solutions are open source now. They're completely on GitHub. The link that you see on this slide, you can check out. You can learn about how, you can see their solutions, but also all of the winning teams created YouTube videos, which are also, the links are also on GitHub, as well as a seminar. There's an ASHRAE seminar that they also presented. The top 3 teams also presented in even more detail, up to 20 to 30 minutes of explanation. So lots of really interesting things in there that we learned. Here's some of the top, I would say these are the top 4 insights that we learned from that competition, is that number 1, it wasn't a single machine learning model, it was an ensemble of models. And this is consistent across the entire top 100 teams. But the top 5, we learned a lot of detail about their ensembles. On the right here, you can see some schematics that were created by the top 2 teams that show basically you have the training data, the feature engineering, and then you have these breakouts of various models. So they basically trained multiple models with multiple configurations of hyperparameters, multiple model types. Most people used gradient boosting tree models as the main set of models, including light GBM being like the most commonly used tool in the toolkit. Point number 3, this is really interesting. Really, the top winners themselves differentiated themselves by pre-processing the training data in really rigorous ways, really going through removing outliers in a very manual way. And this is really where the engineering expertise came in. The top winning team had one of the participants in the top team had a background in metering prediction. So that person knew that pre-processing was a really big part of really winning a machine learning competition in a sense. So lots of really interesting stuff. And there's a paper that you can check out to see all those details. It's not just about the top solutions. We also aggregated a lot of the statistics about all of the content created. So at the end of the day, Kaggle is more, it's a social media platform as much as it is a machine learning competition platform. So people are able to create what's called notebooks. These notebooks are machine learning or workflows that are either Python or R programming language based, and they're freely available to the world. So, and a lot of those notebooks are what's called starter code notebooks. So we saw this as one of the, I think this, for me personally, this was probably the biggest and most interesting output of the whole competition, was the sheer amount of content and tutorials and what I call recipes of analysis that are analyzing data from buildings. So if you're somebody that's coming in looking at this competition, I would highly recommend to check out the discussion boards and the notebooks before diving into the really complex top 5 winning solutions, which are really, really complex. One of the things that's happening right now, some ongoing work, there's a paper that's that we're almost ready to preprint in the next week or so. We should have it out, where we're going through and analyzing the errors that occurred. So we basically took the top 50 solutions. We compared these solutions to the ground truth test data. We created these categories of error types. And the categories are based on the characterization of the error, how long the error lasts, what the magnitude of error is, and from a single site, did that error occur on lots of buildings from the same site? So this is kind of a teaser slide here. I won't get into the details because it'll take a lot to explain what's going on here. But we ultimately, the big takeaway is that in the entire test data set, about 80% of the time, the top models in this competition had what we considered to be quote unquote a good fit within a certain range of error. And then the other 20% we categorized into sort of these, what we call in-range and out-of-range errors. In-range errors being errors that probably can be fixed, by adding extra data to the models or tuning the models, and then out of range errors, which are catastrophic errors probably due to sensor failure and things that you just cannot probably ever predict. So keep an eye out for this paper. The preprint, like I said, hopefully we can get it out in the next week, and some interesting stuff that's going to be in there. So moving on now to the next kind of area, data, getting more and better data for machine learning research. So this is also has a data-driven focus as well. Please keep that in mind as I go through these next few slides. And these slides, I kind of defer a bit to a kind of famous professor in the field of time series data mining and machine learning in general, Eamon Ko. He's a professor at UC Riverside. And he's kind of throughout the last 10 years has been one of my sort of idols in a sense from the machine learning community. He has really amazing tutorials, and he shares tons of stuff on his website. So I've included a link to the slide deck, which I'm going to show a few slides that from his one of his talks, because I think that they really encapsulate some really interesting ideals that I think in our field we can also learn from. And he has a slide that really resonates with me about what makes a good research problem. Please also remember, this is in the context of machine learning. This is from the machine learning community. So he's suggesting that your problem, of course, is important, that you can make progress, that there's clear metrics of success. But one of his really big suggestions to the machine learning community is always use real data. So if you're training a model, try to always make sure that you're using real data to train that model. And this is the reason I like Eamon Ko's his slide decks, is he has slides like this. You know, he says, for example, there's a huge difference between you know, training a model using random data created by a MATLAB script versus what this researcher did was glue a tiny transmitter to the back of a Cricket to actually create those data sets. And he really talks a lot about, you know, in the machine learning community, you know, using real data, creating that data if you can't find it. And some of his arguments against using synthetic data for machine learning research is that, you know, we don't know, and you may not think this is a big deal if you're doing it, but the readers of your papers are not really going to know exactly how that synthetic data set was created. They don't know how many data sets maybe you created. And Eamon makes the argument that at best, your making of your own test data set is sort of a conflict of interest in a sense. He also brings up another pitfall. Synthetic data can lead to contradictions. And I've seen this in the building industry. I've even, I think, been guilty of it maybe once or twice, is in a paper saying, this paper is important because we need the ability to process large data sets because it's becoming more important. There's more data out there. And then in the exact same paper, we say, because of a lack of publicly available data, we created a synthetic data set, which we use to train models. So I don't, you know, this is something that's really, this slide kind of cracked me up a bit because I think that this is something that, you know, is something that we struggle with in our community as well. And it's not intentional. I don't think it's intentional, but I do think it's something that is a problem in a sense. So Eamon says, okay, in his community, where do they get good data? Well, you can get it from data mining archives, from different sources, from expert collaborators. You can make it yourself by strapping the sensor to the back of the Cricket, or in our case, you know, obviously collecting data from buildings. So going back to our industry, what about us? Where do we get good data? And this is something I've also struggled with over the last 5-6 years or more, is where to get data. So this is really the Building Data Genome Project, as Adam mentioned, is something that I've been working on for about 5 years. So the next generation of the Building Data Genome Project is the 2.0 version, which is really just the data coming out of this Kaggle competition. So please check this out. There's a scientific data paper about it. There's lots of co-authors because there's lots of people that helped collect and curate and process this data set. This wasn't done, the Building Data Genome Project 1.0 was really mostly just me doing it by myself. Now Building Data Genome 2 is kind of a small community. And as you'll see in the next few slides, I'm keen to grow that community. So energy data, BMS data, all kinds of data sets, we need to start sharing and aggregating and creating more open data sets. Making data is becoming easier. This is a little bit of a tangent, but I wanted to swoop over to what's called the Cozy platform. This is a smartwatch-based app, which is an open source project. The reason I think it's important in this context is that with tools like Cozy, we can collect more and more data across more and more places and have that data be somewhat consistent and create really large data sets. Cozy is what's called longitudinal intensive method, which means collecting multiple data from the same person. You can ask questions about thermal comfort, which is the most common thing we've been doing, but also now we have question sets related to privacy, distraction, exercise and movement in the built environment related to wellness. We have a new question set about the perception of infectious disease problems. So anyway, creating more data is the key, essentially. And then this is a screenshot from the Kaggle platform. So beyond using Kaggle for machine learning competitions, it's also useful to store data sets in Kaggle. So they have what's called data pages in Kaggle. And here's a screenshot of the data sets that I've uploaded to Kaggle. And people can analyze these data, they can play around with them, they can do various things with them. Not all of these data sets are mine. In fact, out of this list, I think only 2 or 3 of them are from my lab. The rest are actually open data sets that I give attributes to the creators. I put them on Kaggle's data platform, and people are able to play around with them, use them, upvote them, all kinds of interesting things. So Annex 81, IEA Annex 81, this is something I'm helping to lead within one of the activities in Annex 81, is to further develop this, what I call sandbox. So if any of you out there have data sets, you want to share data sets, please put them either in a GitHub repository, in a Kaggle data page, or both. And send me an email, send me a message, tell me where they're at. And I would love to start growing this sort of library of different types of data sets. And with Annex 81, we're also looking at like sort of hackathons and ways, basically if we get together in a group, we can start playing around with the Kaggle data pages. There's other functionality such as creating what's called tasks in Kaggle. So you can actually say, what are the questions that you want to try to answer from this data set? And people can create submissions to those tasks. So I'm kind of rallying a bit here, trying to get people in our industry to share data, to aggregate data, to do whatever they can to create more and more open data sets so that we can grow in this direction. Some of you may have stumbled across this. There's also an edX data science course that's been online now for about a year, which is really focused on getting people started with Python and pandas in the direction of analyzing data from Kaggle data pages, and Jupyter notebooks really in general is the format that we use. Over 20,000 people have gone through the course in the last year. Lots of really good feedback. I'm in the process now of renovating the course to make it more relevant and more interesting. So stay tuned in 2022 for possibly a new set of content. But the existing course is going to relaunch in August of this year and run for about 6 months after that. So, and you'll still learn quite a bit from the old content, don't worry. Yeah, if you're interested in learning Python and pandas, please check that out. Okay, so those of you that are really from the simulation side, of course, the white box modeling side I want to talk about. I really think that there's a few directions of white box modeling or gray box modeling, which I think is really interesting, that are looking at a much bigger picture, much more scaled application of simulation, which I think is a really cool direction, which really gets us towards that big, compelling objective. The one that really stands out in my mind when I talk about this is an effort being done by the Oak Ridge National Laboratory, specifically Joshua New and his team, which had the objective to create an Energy Plus model of every single building in the United States. So as far as I can tell, they succeeded. I haven't talked to Josh for a long time, but it looks like they have published a new data set. You can see the links here in various papers and links where they do have a data set of over 122 million buildings that are Energy Plus models of every building in the United States. So lots of really cool things that they're doing with this data set, or they plan to do with it. I think this is really a step in the direction of, sort of this like interesting, really highly scaled white box modeling technique. So, if you create all these white box models, how can you, the title of my talk and the thing I'm trying to promote is convergence between these two paradigms. So here's a really good example of that. And this is a paper that I was fortunate enough to be to assist with a team from Stanford, Rishi Jain's team, where we were taking different types of white and black spot models and converging them. Really the key visual abstract you can see here, we're taking annual measured energy data from buildings across Manhattan. We're taking white box modeling, so basically energy plus models that were created for all of these buildings. And we're trying to use both of these types of techniques to create synthetic hourly profiles of each building in Manhattan. So there's various uses. If you check out the paper, we give some interesting insights on what you use those synthetic profiles for. But there's lots of interesting directions you can go in. But I think that's really, we found kind of an interesting way to actually try to converge these areas in a scalable way. Another interesting example is a study done at TU Delft. This is a master's student, Chen-Kai Wang, who I also had an opportunity to be a co-advisor for his master's. He was doing something very similar, building a physics-based model. In this case, he used a simulation engine called eSim, and he was calibrating that using measured data. And the goal was, taking lower granularity measured data, like at daily and monthly levels, and physics-based models to create higher granular synthetic data. And he did it in the heating context. He had various applications. Here's a publication from last year where he goes into some details. And I think this is really also a good example of that modeling at scale kind of aspect. Okay, so I'm running down on my time here. That's great because I only have a few more slides. I really want to get back to, and I want to leave you with that question the autonomous vehicle industry has really created that, I don't want to call it hype, but it kind of is. They've created that momentum to get companies and of course also research to invest large amounts of money. So in the building industry, how can we also potentially achieve that kind of momentum in our fields and get companies to really start, using our research in that way? So here you can see on the right are two figures now hugging and working together as opposed to fighting or duking things out. I see this as kind of like us researchers as well. We get the white box and black box model folks. Let's get together. Let's figure out how we converge what we do. But I do think that, to really get this kind of momentum, like the car industry has gotten, we focusing on generalizability, focusing on techniques which go beyond our comfort zone, which is case studies, looking at open data as a catalyst for that, larger scale simulation frameworks. And then last but not least, probably the most important thing is really identifying a very clear, easy to understand, but very compelling objective that we all kind of try to maybe get behind. I don't know if this is possible. I put an example here that I think maybe is something we could discuss. An example might be driverless buildings. So, being able to come into a building and AI being able to identify what's happening in that building, what are the systems, how, labeling the points automatically, finding the patterns automatically, doing things in a way that's automated. This is synonymous to the road networks. Every road is different in the world. Every building is different in a sense. So I don't know if this is the right objective, but I do think it's something that's maybe relatively easy to understand. And it's something that we could try to drive towards, something very compelling that our field could try to go towards, I'm suggesting. So thank you to everyone who sat through. Hopefully everyone had a cup of coffee, was able to click around on links. I also want to make a very strong thank you to lots of people who helped with this research. It was not just me. There was lots of people from my team as well as collaborators, the people from CAGO who helped us, the people from ASHRAE technical and operations and planning committees, and then of course the research funding from the Singapore's NRF, National Research Foundation, and from collaborators at the BEARS, Berkeley Alliance for Research in Singapore. And with that, I will take any questions. I think I'm maybe just in time, and I hope everyone can hear me the entire time.
Can hear you great. And thanks, Clayton. Fantastic presentation. We already see some of those comments coming in. I've made a comment in the chat. If anybody has a question for Clayton, feel free to write it down. I think there's one question from Jose right there in the chat for you already, Clayton. I'm sure many others will follow. And if anybody would like to ask a question via audio, just raise your hand and we'll unmute your microphone as well.
Yeah, so for Jose's question, that's a great question, and I'll try to answer it based on what he typed out, and then if he wants to verbally follow up or anything, that's also cool. So Jose's asking, yeah, do you have some ideas for developing business models? Yeah, okay. So I brought up you know, private investment in industry. So I think you know, getting to that clear objective like the autonomous vehicle industry has is something that companies, it's a sort of chicken and egg problem, I feel like, where companies are not, let's talk about big companies. Big companies are not quite sure where they should invest money. They kind of want to, I feel like I get that vibe that there's this, where does ML and AI fit and how can it improve the way we do things? And at the same time, the customers are not sort of begging for certain things. So it's I don't know, it's kind of a chicken, like I said, chicken and egg type of issue. So personally for me, I mean, it's to see the big companies invest that kind of money, they're probably needing to see the market ask for it. Okay, so smaller companies, so if you talk about maybe smaller, maybe startups, maybe medium-sized companies that are more nimble, who can invent new business models, I think there's a lot of opportunity there. But at the same time, and there's lots of cool ideas out there, but at the same time, the industry is extremely slow, right? So startups have a really, really hard time in the building industry because it's very, it's really, really slow. There's a lot of stakeholders, a lot of decision makers they have to go through. So yeah, I think let me try to answer your question. What are some of these ideas? I think that if people start having a bigger voice in buildings, so if we give people occupants more of a voice, if occupants can say, hey, I'm too cold and I live in Singapore and that's ridiculous, right? Like it's over conditioned in here. I wear a jacket every day. If these messages start to become more meaningful and more, you know, something that people who lease buildings actually listen to when they look at buildings to lease, that can be a catalyst for a lot of investment in AI and ML and things like that. So I guess I don't have a clear idea on a business model, but I do think I have a clear idea on maybe a trigger that could cause business models to be, you know, profitable, let's say. Yeah, I'm kind of late night rambling now. I think I'll just, hopefully I helped answer Jose's question. It looks like we have a few other questions. And Adam, feel free to, you know, I know
no, you're doing a great job. And in fact, I mean, the next two questions, I can't wait for your answer on them. These are questions that we could discuss for a long time about. So feel free. I feel convinced to like read these out as if we're an auditorium, but I think we can all read the question. Go ahead, Clayton.
Well, so the next question, from Seper, garbage in, garbage out in the age of big data. So how do we filter through the exponentially growing volume of garbage? Yeah, that's a great question. There's a really good book that I read that was written. It's not a new book. It was written like 9 or 10 years ago. It's simply unceremoniously simply called it's called Big Data. And I'll double check that and maybe put it in the chat later if I go find the book. That book is really great because it really, and you can find dozens of books like this. These books are describing how AI and big data have transformed certain fields, specifically marketing and advertising and retail. right? We all know Amazon, we all know Google and Facebook, and we know all of these areas or industries that have been disrupted using big data. And that book does a really good job of explaining how garbagey data actually produces better predictions than smaller amounts of good data versus larger amounts of crappy data. The bigger amount of crappy data always wins. And they give a lot of good examples, like how Amazon created their recommendation engine for their platform, how Google created Google Translate. Maybe if anyone remembers, back in the early 2000s, it was a race between Microsoft and Google between who would have a better translation engine. Microsoft's approach was to hire linguistic experts to really really identify what are the nuances and train models based on the nuances of language, whereas Google was just scraping web pages of various languages. And Google's platform ended up becoming the more accurate one. And so they talk about the nuances of that. They talk about like how this actually works in practice and things. And so that's kind of how the inspiration, because in our field, we don't really have big data yet, I think. I mean, it depends. I think that the auto BEM thing I mentioned that Oak Ridge has worked on, where they're modeling every building in the United States, that might be getting close to where you could start calling it big data. But the stuff that even like the Building Data Genome 2 project, that's not big data. If you can load the entire file into the memory of your computer, it's not big data. That's my opinion. That there's no definition, I would say. But anyway, so to learn about this garbage in, garbage out thing, I think it's great to look at analogies, look at other industries that have taken large data and transformed it and made it useful. But they didn't do it with just data. They also had, I also want to emphasize, it's not just about getting tons and tons of data and just throwing it in an engine and then out comes the perfect thing. No, there's a lot of there's a lot of experts, there's a lot of domain knowledge that gets built into this. So Google also had language experts as well, right? But they just did it in a slightly different way. So I do want to be very clear about that. And these books do a really, really good job of explaining that as well, better than I'm doing right now. So, okay. Wow, people are popping up everywhere.
Now you're getting, I can help. You're doing a great job, Clayton. You're going to get a lot of questions now. I think the next one is from CTL. Thanks, Clayton. How do we encourage companies to donate more data? What is the value proposition to them?
Ooh, yeah. Oh, man. If I knew the answer to this question, I'd be doing it right now. I'd be doing it right now. Yeah, it's a really good question. The low-hanging fruit are definitely entities that have something to gain through sharing data, which are university campuses, companies like Google and Facebook and these big companies. They'll share. I've seen data sets sometimes from corporations that understand the value of open data and what it can do to help things. How do you get your average commercial building owner to share their data? What are the incentives behind that? Oof, I don't know. Pay them? Maybe. Yeah, that's something. And going back to that other question about business models, maybe the person who figures out the best way to incentivize data being shared is the person who's going to create the best models and blah blah blah. So that's a great question. I don't know the answer. I just know that there's low-hanging fruit out there, which are mostly research entities like university campuses that are usually pretty open, but it's very hit and miss. Some university campuses publish all their data online for everybody to see, no matter what. Other universities keep it locked away and don't share it with even people within the organization, NUS. So, yeah. So I don't know. That's a great question. I don't know. So, but I would love to chat about it sometime.
And then when Clayton figures that one out, he can tell all of us, and we'll
yeah, we can all go out and collect lots of data. But I think every little opportunity, the other thing is that every opportunity we as a community have to collect data and share that data, even if it's small, kind of grows and grows and grows, because people can go in, they can aggregate the data sets like we did with Building Data Genome. You can create bigger data sets and this has happened with the ASHRAE Global Thermal Comfort Database 2, which happened recently. That's not industry data, that's research data, but that's a good example. And then now there's a big effort in the ASHRAE Global occupant behavior database, which is under development now. So more of these kind of efforts, and every time you as an individual researcher share your data, the more likely it is that we can build bigger and bigger data sets. So bottom up, I guess. I don't know.
Thanks, Clayton. I see the next question is, what are your thoughts on privacy issues regarding collecting data in buildings, specifically about occupancy?
That's a great question. I'm going to try to artfully dodge it a little bit by saying, like energy data, we have always done our best to make sure it's aggregated enough that it's never going to show human behavior. We focus on commercial buildings, we focus on whole building meters, so we've been able to avoid that for now. On the occupant side, so I brought up Cozy, right? So Cozy is a research tool right now. And every time we deploy Cozy, we have an IRB, we have an ethics review, we have a consent form, we have data being stored very, very properly based on the IRB. So we as researchers are doing a very, very careful job of making sure privacy is well considered under the IRB, which is a very rigorous process. If I'm a company and I want to use Cozy, and we've had tons of discussions with actual companies about this. If I'm a company, I want to use Cozy, how do I deal with these issues? Well, you have to figure that out as a company. You have to talk to your lawyers. You have to, there has to be terms and conditions. Maybe you have a consent form as well. And Cozy does have, Cozy Apple does have a built-in consent form. I think, something like Cozy could be deployed at a mass scale commercially. It is open source. It is an open source project, but it could be deployed commercially if people are giving their opt-in consent for certain types of data. Apple actually does a pretty decent job of giving people the power to share only what they want to share from their watch and their phone. So that's been really helpful to try to explain to business owners. But long story short, just like the business model question, just like the sharing data question, this is a big, hairy problem that we've been able to artfully dance around because we're just, little researchers that don't have time to solve everything. So, but that's a great, great question. Yeah.
Great question. I think I see the next question, and apologies if I don't read out the comments. I think we can read the comments up from Benoit. Thanks, Clayton. Deploying data-driven solutions can be resource intensive in terms of computing power. How do you see the deployment of these solutions, coupling between IoT devices, edge devices, gateway, cloud infrastructure? What would be the most efficient way to deploy?
Yeah, so I mean, I can generically describe some technologies that we've been using in the past years, and I know Adam and a lot of people have been using these new technologies that are really, for example, time series databases. This is something that's become very popular in the last 3 or 4 years. They are designed for IoT, so they're designed to ingest huge amounts of time series data from IoT devices. And do it very fast, do it without creating, it's a schemas created on the fly. And people like me I would not call myself a database expert. I'm able to set one up, right? So, but it also kind of goes back to like the amount of data that we're actually deploying in buildings is still compared to other domains. Like if you look at the amount of data that maybe Amazon collects from its users, we're still just a fraction. We're still just very small peanuts compared to what other domains are doing. So, but time series databases have helped a lot. People talk a lot about edge computing. I think edge computing, it's really fun when it comes to computer vision. So I think if you just have a sensor that's collecting data, I don't think you need edge computing because it's not that much data. But if you're taking images, there's a data issue. There's also a privacy issue. So edge computing can help you transform those images into insight that's protecting the identity of people and stuff. So there's all kinds of new things kind of working their way into everything. Those are kind of the generic things that really popped into my vision, but there's a lot more than that. I brought up 5G. There's this 5G lab here in Singapore. So we have a few professors that are looking at, okay, with that kind of bandwidth and that low of latency of your connectivity, what are the things that get open? What are the opportunities that open because of that? And they're coming up with all kinds of cool ideas, most of them related to drones and all kinds of inspection technologies and fun stuff. So not enough time to answer that question. Also a big, very good question, but also a big crazy, hairy question that would take a lot of keynotes to figure out. So yeah, thank you for that question.
Okay. The next question I feel compelled to ask, I still think, Tom, it sounds like a little bit of a plug. Hi from Ecobee. We have 6 terabytes of smart thermostat data our customers have donated to our research partners. How can we help building researchers make best use of this and help us save terawatt hours?
Yeah, I've heard of that data set. I haven't got a chance to check it out. But
Same
lots of cool papers I've seen, people using that data set. So, I mean, short answer is, Tom, just keep doing what you're doing. I mean, get them, because we also have a chicken and egg problem in the research community. So people are just now starting to understand the value of these bigger data sets. So sharing that with a few researchers, and I think you're sharing that data with some really sharp people who are writing some great papers. Once our community starts to see, oh, that's cool, that's interesting, starts building and building, then I think it's a situation where our community starts saying, okay, here's the home we're going to build for. I mean, for me, I'm building this like library. When people send me an email, I slap it in a Google Doc spreadsheet. You know, there's something really sketchy, you know, not sketchy, but like half-hearted thing that I'm doing now just individually. But as a community sees more and more value in this, we'll start, I think, creating more concerted efforts. And then at that point, we'll say, well, we know Ecobee's got some awesome data. Let's put that data in our little home for all of these data sets and stuff. So keep doing what you're doing, and then eventually we'll, you know, I think we'll meet in the middle somewhere. Yeah, that's great. If I had much more time, I would play around with that data if I could. I'm sure a lot of us would. So.
And our next question coming from our fellow co-host, Ralph, how could we be embedding our knowledge of building physics into machine learning models? And so how could we probably be better at embedding our knowledge of building physics into the machine learning models?
Yeah, that's a great question. That's really where you really start getting into, there is research in this area, and probably some of the people in this group, where you're actually creating, like in deep learning, you're creating the structure of the neural networks based on physics principles and things. That's one way of doing it, which I think is interesting. I'm not an expert in that area, but I think it's kind of cool. There's the calibration. I think calibration, like that's a really kind of contemporary, like it's been around for a long time, but when you talk about calibration, that's essentially kind of what you're doing is this merging. It's kind of after the model. So you're not merging the models in the way they work together, and in the guts of it, you're kind of doing it afterwards. So then there's the calibrations kind of approach, and there's lots of cool innovation happening there. And I know, like, yeah, Adams, your team has done a lot of that stuff over the years, and people, various groups have done that. And then there's there's even a step beyond that, which is like training, like what Tesla and Waymo do, where they even they create simulations. They use physics-based data as well as data-driven data, and they create probably ensembles, just like in the Kaggle competition, the winners created these ensembles of models. I think that's also a really interesting way to try to get building physics into the machine learning process. But they're just different levels of that interaction happening, just different areas where that interaction happens. I don't know what the right answer is. I don't know which one's going to work best. I think the community, you guys figure that out, we will figure it out. But those are just the categories of innovation in those areas that I'm familiar with. Yeah.
Clayton, I have one question for you, which we didn't ask. I mean, I definitely kind of, shoot from the hip, off the record, even though this is being video recorded in front of 101 people. Now, the $101 billion projection exists. What are your thoughts? You had the slide about the kind of fight between building simulation and building kind of data analytics for consultants and those in practice, and for this sort of building performance design consulting industry writ large. Are these two sectors going to be mutually exclusive? Are we going to see not a downsizing in simulation, but perhaps a move increasingly towards completely different techniques from the way we've been doing simulation in the past? Or will we see efficiency and sort of a lot of this sort of hypey fluff of machine learning might go out the window, and we'll get more to really more the applied? I mean, that sort of industry forecast, your views on that, I think, matter, and be interesting to know what you think.
Yeah. Yeah. You want me to go out there and make a stand, I guess, right? I'm just kidding. No, I think if you look at the simulation, like if you look at the practitioners who actually perform simulation services, you still see a lot of these, the kind of stuff that pays the bills, right? You're creating models for compliance with green labeling, and you have, and now there's this emerging field of using simulation in the design phase, in the early phases of design and the integrated design process and things. I think that those things are still very, very valuable because that's just the way we design buildings. Like we don't design buildings, we don't design 1,000 buildings at once. We still kind of design things one at a time, which is, that's where we really differentiate. This is where we diverge very clearly from cars and phones and computers, et cetera. We have kind of a mandate to create unique, interesting architecture, places that people feel cultural significance because of the architecture. So, and I don't think we should get away from that. We shouldn't mass produce buildings. So when I say that, I think that we should start, really simulating buildings at scale. It's not so much to get, I don't think we'll ever get rid of using simulation in the case study style, nor should we. It's just more that there are bigger picture questions that I think are being not answered, that there is no business model that it doesn't pay the bills right now, which is why you don't see any, but I hope in 10 years, maybe sooner, you have these entities that do simulation doing both of these directions. So they're doing design phase, sort of integrated design process modeling for individual buildings, as well as using their expertise to do these more scaled things. And we're never going to get rid of industry experts. There's a lot of, if you read these, there's another really good book called Prediction Machines. So I mentioned a book called Big Data. There's another book called Prediction Machines. That book also is really, really good at describing this, because people say, well, we don't need experts anymore. We just take enough data, throw it in enough engines, and we get enough amazing results, right? But these books do a really elegant job of explaining why we are always going to need experts. Industry and domain understanding is always going to be important. And it comes down to human beings being better at judgment than machine learning will ever be. AI and machine learning will never have the human's ability to make judgments based on what's important to that human or what's important to a group of humans. So the book Prediction Machines, that's a great book to read. It really helped diminish a lot of the fears that I had about how machine learning is going to impact our industry. There's not going to be mass unemployment of architects and engineers anytime soon, just like there wasn't mass unemployment of accountants when computers came along in the first place. Accountants used to just add up numbers. They didn't do anything but add up numbers. Now accountants do lots of interesting things, but the computer does all the adding. So the Prediction Machines book is a great place to dive into these hairy ideas, anyway, I'm just going on a lot of different paths, not really answering your question very directly, but I hope the industry expands and we offer different services, but we'll never get rid of, in my opinion, the design process. I don't think that's possible, nor should we, because we don't want cookie cutter buildings, basically, right? So yeah,
I think you answered that very well. And Prediction Machines, which you mentioned, and I sadly haven't yet come to read it, and yet I know that I should, and probably anyone, especially if you're a graduate student on this call, you should read that book.
It's a pretty manageable book. It's not too thick. The big data one's pretty thick, takes a long time, but Prediction Machines quite concise. I think, yeah, I highly recommend that book. It really breaks it down in a very simple way. Yeah.
We have one more question in the chat, and I think that will be our final question for a variety of reasons, including knowing exactly what time it is in Singapore right now, from Kevin. Any thoughts on metadata and buildings? Do you anticipate an increase in metadata that can help add a Y to the energy or comfort data we're seeing?
That's a great question. I have a much better direct answer to that than I did the other. This is a little more specific, or yeah, question that I'm more equipped to answer. So metadata of buildings is actually becoming the objective. When you look at scaled data analysis of lots and lots of buildings, predicting a building's metadata is harder than getting its energy data. So let me explain. The smart meter deployments across Europe and America, and maybe even Canada, I'm not sure, but have been huge in the last 10, 15 years. So for example, with smart meters, we know exactly how much that building is using, energy it's using on a 5-minute interval. We know exactly, every detail of how it's using energy, but the utility that collects all that data doesn't even know if that building is a grocery store or an office building. It just knows where they know where they send the bill, right? So they have all this intricate time series data, but they don't know much about the building. So I've done a little work in the past of inferring metadata about buildings using time series data features as an input with some success. I wouldn't, there's a lot of work to be done in that area. But I think that's one of the really interesting things. It's just like the way Amazon builds models to predict things about us humans. They're really trying to predict things about they're trying to predict classes and they're not trying to predict, like a value. They're trying to predict whether we want to buy something or not, right? So in buildings, it's the same thing. We need to figure out ways to also get classification as a machine learning objective more prominently, because it is a cool area, and yeah, I think it's interesting. Anyway, maybe I didn't answer that question so specifically, but my brain is starting to fail.
I heard metadata is the holy grail of a bit of the future.
It's a cool area. It's overlooked. It's overlooked. Yeah. It's a cool area. I like that.
Clayton, we're just approaching time, and I think this is a perfect way to end a really interesting, great, and also riveting discussion that followed your keynote presentation. It gives us all a lot to think about. It also really satisfies and fits perfectly with the conference theme. And we're so happy and grateful that you've been able to make the time for us. As I said before, if anybody were to Google the time in Singapore right now, it's well past the bedtime even of tenure track faculty. Clayton, thanks very much for being here with us today. You are free to stay with us throughout the rest of the conference, although I fear we'll probably lose you in a few minutes.
Might hang out for a bit longer. Thank you very much, Adam and Ralph and the team for inviting me. This is it's been great. I love sharing this stuff. So everyone, my slide deck, reach out to me by email if you want, and send open data sets, send links to open data sets. I'd love to hear from everybody. So thanks, Adam.
You're here. Thanks, Clayton.